We have two and a half more reactions of amines that we're going to look at before this chapter is done. And this section we're looking at reactions of amines with nitrous, not nitric, nitrous acid. Nitrous acid is HNO2. And it is extremely reactive. So it is usually prepared, what we say, in situ, kind of like a Grignard. Well, exactly like a Grignard. Oh, that is not the right way to spell that word. Prepared. HNO2 is prepared in situ. Just like a Grignard, we prepare it in the place that we need it, exactly when we need it. We don't prepare it in advance and store it. And again, this is because of its reactivity. It's easy to make, just like Grignards are easy to make as well. We're going to take sodium nitrite, NO2, not nitrate, and just simply react it with hydrochloric acid, and we'll get the nitrous acid, HNO2. Now the nitrous acid, because it is very reactive, it pretty much immediately decomposes, and when it decomposes, it forms water and it forms NO+, a cation, and there is some chloride anion left over that came from the hydrochloric acid originally. This NO+ ion is called the nitrosonium ion. And even though we say that we're looking at the reactions of amines with nitrous acid, we're actually looking at the reactions of amines with this nitrosonium ion. That's really our reactive species. If you're curious about how this happens, you've got a picture of the mechanism of this reaction in your book. It's 23.2. So it's starting with the sodium nitrite reacting with hydrochloric acid, showing you the structure as well as the formation of nitrous acid, and then the decomposition of the nitrous acid to form the nitrosonium ion. So here you get a picture of what the nitrosonium ion looks like. There's its predominant resonance structure. So once we get the nitrosonium ion prepared, it can react, the NO+ can react with primary and secondary amines. It doesn't react with tertiary amines. We'll look at the mechanism for that, but basically you need to have a hydrogen on the nitrogen for this type of reaction to occur. So first thing that we're going to do is look at the reaction with the secondary amines. So we're going to start with nitrosonium plus secondary amine. And this isn't a very useful reaction for us. We're just going to I'm going to draw a generic secondary amine. And the way that we will write this is sodium nitrite with HCl. So even though we know that NO+ is the reactive species, we're still going to write the reagents that we use to generate NO+, and that's the same as with the Grignard reaction. Even though that we know the Grignard reactive species is a carbocation, a carb anion, we aren't writing this as the reagents. We're writing the structure of the Grignard as the reagent. So we're writing NaNO2 and HCl as our reactive species, and the product of this reaction is what we call an N-nitrosamine. So this is an N-nitrosamine. It gets its name because it is an amine with a nitro on the nitrogen. That's what that N stands for in the front of the name. And these N-nitrosamines are not very useful to us. They are strong carcinogens. The N-nitrosamine, this particular reaction is the reason that people are concerned about eating meats with nitrites in them. This is the reason that we avoid nitrites, or we try to avoid nitrites in our diet. As you probably know, the acid in your stomach is hydrochloric acid. Nitrite, sodium nitrite, is a very common food preservative, and meat products are full of amines, amino acids, for example, proteins. So when you put all of these three things together in your stomach, then you do have the potential for this reaction to occur inside your stomach and synthesize these N-nitrosamine carcinogens in your stomach. This is not deterring me from eating bacon, but some people don't want to consume these nitrates for this reason. Here is a mechanism that shows you how that molecule is formed. So starting by showing you the formation of the NO plus group. And then once the NO plus group, it's showing you once the NO plus is formed, it's showing you the mechanism by which the NO plus is added to the nitrogen of the amine, and then deprotonation to give, this is our final product right here. And like I said, that's not a really very synthetically useful reaction. It's got very limited applications. A more useful reaction is the NO plus group reacting with primary amines. So with the primary amine, the only primary amine that actually does this reaction well is aniline. So I'm going to specifically draw aniline instead of just a generic primary amine, reacting again with sodium nitrite and hydrochloric acid. The product of this reaction is called an Aryl Diazonium. It's a fancy name. All that means is that you have a benzene ring. That's the aryl part. Aryl is a prefix that means aromatic ring. And then diazonium. Diazonium is this functional group right here. So it's just this N2 functional group attached to a benzene ring. And for any other R group, so any other primary amine other than aniline, the product, the diazonium that you form, it will decompose too quickly. And sometimes it decomposes very violently. In the decomposition process, we are generating N2 gas, and even though it may not be explosive in terms of flame and fire and things like that, generating a large quantity of gas very quickly can cause your glassware to break or things to be, splattered all over the place. So if you do this reaction, if you're starting with any other type of primary amine and you make the diazonium product, that diazonium product will decompose too quickly for it to be useful for you synthetically. However, the aryl diazonium is stable. You can probably guess it's stabilized because of its resonance, and it is a really useful precursor for a series of reactions that we're going to cover in the next section.